Alright everyone, welcome back to the second edition of Math 371 Coronavirus Edition. Quick reminders that your online homework on MyMathLab is due Friday, and make sure you upload the notes from each class with the problems worked out on Moodle. Let me know if you have any questions. I'm still working on the office hours, and make sure you post any questions you may have on the forum on Moodle. Alright, so let's get started. So today we're going to look at chapter 4.1, and we'll look at section 4.2 later. Today we're going to generalize things that we've learned from the real numbers. So far, we've worked with the real numbers. Or the real numbers to the nth power. These were vectors with n entries. We need to generalize this to what's called a vector space. So a vector space is going to take some of the properties of the real numbers and we're going to generalize them. This is a very common procedure in math where you say, okay, I know how it works with the real numbers. Can I say things that are true in a more general setting? So what's a vector space? There's going to be some kind of picky definitions, but you'll see that most of them are pretty straightforward. So a vector space is a non-empty set. So a set is just a collection of objects. And we call these objects vectors. We have two operations. These operations are addition and scalar multiplication. So you're going to notice a lot of similarities with what we've talked about so far in linear algebra, but they're going to be a little bit more abstract. So the scalars, these scalars could be real numbers, complex numbers, rational numbers. There's a lot of possibilities. If you've taken logic and sets, you might have seen something called a field or an ordered field. The scalars have to come from a field. We're mostly going to be concerned with the real numbers, the complex numbers, the rational numbers, but other fields exist. So the following must all hold. There are 10 axioms. So in order to be a vector space, 10 things must be satisfied. So we're going to let U and V and W are vectors in our vector space, and C and D are scalars. And then the following 10 properties must all be true in order to be the vector space. If I have two vectors in my vector space, then their sum is NV. If I have two vectors, I can add them in either direction. So basically, this is the commutative property of addition. Addition is also associative. So I can add U plus V and then W, or I can add v and w, and then add a u to it. There's a vector we call the zero vector. I don't know what this vector is, but we identify this by the number 0 at the vector over sign. And if I add the 0 vector to anything, the vector is unchanged. All right, we're almost halfway there. So for each vector, there's an additive inverse. And if you take this vector plus its additive inverse, you get the 0 vector. If I multiply u by any scalar, it stays in my vector space. If I take a scalar times the sum of two vectors, this is the same as scaling each of the vectors separately and then adding them. And there's a similar property that holds for when I add my scalars. Or when I multiply my scalars. And last but not least, if I scale my vector by the number 1, it stays the same. So these are the 10 axioms or properties that all vector spaces must satisfy. And we're going to give you some examples of vector spaces. So you need some examples of vector spaces to know that they are very much like what you've been dealing with so far. Okay, so you already know about the real numbers, but you could also have the complex numbers raised to the nth power. These are just vectors where their terms are complex numbers. You could have rational vectors. Those are vectors where the entries are rational numbers. And there are more interesting examples too. So we're going to call an example Pn. These are polynomials of degree n or less with real coefficients, we'll say. Doesn't have to be real, but we'll say real for now. So these are all examples of vector spaces. Some you're more familiar with and some you're less familiar with. So these are some examples, and there are more exciting examples. Real valued functions are a vector space. Taylor polynomials are vector space. Truncated Fourier series are vector spaces. They're all over the place. And if you're currently taking differential equations, or if you plan on taking differential equations next spring, you're going to find that certain solutions give you vector spaces. Okay, so we have some things that we can prove. So the first proposition is the vector 0 is unique. That is, there can only be one 0 vector. Well, let's prove this. So suppose there were two zero vectors. The zero vector A and the zero vector B. Well, let's add them together. Since 0A is the zero vector, if I add anything to it, it stays the same. So, because this is the zero vector, this is the consequence. However, we also know that if 0b acts as the zero vector, the same sum must equal 0a. And so these are equal. And this tells us that there can be only one zero vector. So if you did have two, you can do a little, dance here and show that there must only be one. Okay, well that's great. So let's practice another proposition. These are basically skills I want you to develop that you will find very useful in logic and sets. We have some definition that you're not familiar with, and we want to prove things with it that you might think are obvious, but aren't actually obvious. They require a little work. Okay, so let's do another example. Okay, we want to prove that 0 times u equals the zero vector. How can we do that? Well, I think the easiest way of doing this is just to start with this vector right here. 0 times u is the same as 0 plus 0 times u, which is 0 times u plus 0 times u. We know that every vector has an inverse, so we just add that inverse to both sides of this equation, and we know that every vector plus its inverse is the zero vector. So the left-hand side becomes the zero vector, and the right-hand side becomes 0 times u plus the zero vector, which is just 0 times u. And so this tells us what we wanted to, and that's the end of that proof. Okay, so this was the proof of the second proposition. So you can see here how these properties we're using come from the properties of the vector space. So let's look at another example of vector spaces that you've also encountered before. And these are the domain of subspaces. Okay, so we've seen a subspace in the real numbers to the n. Let's see what it looks like for a vector space. So a subspace is a vector space. Well, a subspace of the vector space V is a subset H of V with three properties. So a subspace is going to be some sub-collection of our vector space V, and it's going to have three properties. The zero vector of V is an H. H is closed under vector addition. What does that mean? Well, it means that if we have two vectors that are in H, then their sum must also be in H. Basically, if I have two vectors in H, I add them, it must stay in H. And last but not least, H is closed under scalar multiplication. Okay, so that just means that if I have a vector u in my subspace H, then this tells me that if I scale u by any scalar, that's also in my subspace H. A couple remarks about subspaces. A subspace is actually a vector space in its own right. And every vector space contains the zero subspace. The zero subspace is the single vector that is only composed of the zero vector. It's the subspace composed of only the zero vector. Okay, so I'm going to give you two examples, and you're going to you're going to think about whether these are examples of subspaces. So, examples. Is the set of vectors of the form 5b plus 2c, b and c, a subspace of R3? This is where b and c are any possible number. So I want you to pause the video and think about, is this an example of a subspace? And then I'll show you the answer in just a second. So go ahead and try to figure it out, and then I will show you the answer. So now you've had a chance to think about it, the answer is actually yes. So the first question is the zero vector in here? Well, the answer is yes. Just pick b equal to c equals 0, and you pretty clearly see that this is in the subspace. Okay, well, what about the second one? What if I have two vectors in my subspace? So what are these two vectors that we're talking about? Well, every vector must look something like this. I'd pick a number for b, and I'd pick a number for c. So I'm going to pick the following two. In the first vector, I pick some number b1 to go in the b place, and I pick some number c1 to go in the c place. And I add these two vectors, because the second vector is obtained by putting b2 in for b and c2 in for c. Well, if I add them, I can rearrange the terms and I see that this is also in my subspace by setting b equal to b1 plus b2 and c equal to c1 plus c2. Okay, so now I've shown that's closed under addition. Now let's consider scalar multiplication. So let's scale, we'll call it by d, my vector, and I can write this as 5 BD plus 2 CD, BD, and CD. And I see that this can also be obtained by plugging in particular numbers for B and C. And so this tells me that this is a subspace of R3. In fact, you know this subspace well. It's actually equal to the span of two vectors, the vector 5, 1, 0 and the vector 2, 0, 1. That's another indication that was a subspace. It's the span of two vectors. All right, well, let's take a look at another example. Is this a subspace? Is the set of polynomials a subspace of P2, polynomials of degree at most 2. Go ahead and pause the video and think about it. All right, well, what do you think? The answer is actually no on pretty much every front. There's no zero vector. No matter what I plug in for A, I will not get the zero polynomial. It's not closed under addition. Because I clearly see this is not an element of my space. And it's not closed under scalar multiplication either, because nothing works out for this one. None of these elements are in the space up here, H. So this is not an H, and this is not an H. So this is not a subspace. Okay, so now it's time to introduce a few concepts that you've seen before, but we need to define them in the vector space arena. So, a subspace spanned by a set. You're going to see that these definitions all match exactly what you've seen in the past. So, if we have some vectors that are in V, then a linear combination of them means the same thing as it did before. So we see that the span of these vectors is just the set of all possible linear combinations. Okay, same definition as before. And we call this the subspace generated by these vectors. So that's a definition. We've actually encountered many subspaces of vector spaces before, and I thought we would go through a couple examples before we move on to other subspaces. So let's look at a matrix and see that we've encountered this before. So the first example is the null space of a matrix. And the null space of an m by n matrix well, you write that as null A is the set of vectors x such that ax equals the zero vector. So this is a subspace of Rn. And let's show why that's the case so that you can see what goes into showing something as a null space. So the first question is the zero vector in the null space? Well, of course. A times the zero vector is the zero vector. So the first condition of a subspace is satisfied. Is it closed under addition? So let's assume that we have two vectors that are in the null space. This means that ax equals 0 and ay equals 0, and therefore a times x plus y is just ax plus ay, and it's pretty easy to see that that is the zero vector. All right, so now we just need to show one more condition satisfied in order to show that the null space is a subspace, and that is showing that it's closed under scalar multiplication. So if we know that x is null in the null space of A, then this tells us that A times C of x, or C times x, is the same as C dot AX, which is C dot 0, which is the zero vector. So this tells us that the null space is a subspace of Rn. So why is this important? Well, anytime you can show that a set is the null space of a matrix, you have shown that it is a subspace. All right, excellent. So let's do this with an example. We're going to show that something is a subspace by showing it's actually equal to the null space of a matrix. So let's let W be the set of vectors of the form well, let's see, these are vectors in R4 such that A minus 2B equals 4C and 2A equals C plus 3D. We want to show that this is equal to the null space of some matrix A. So it's helpful to rephrase these so that we have some equations where everything non-zero is in one side of the equation, and we just have 0 on the other side. So now we need to write a matrix that has these two conditions satisfied. We want a matrix so that if I multiply it by a vector of this form, it equals 0. So you should be able to just read off what this matrix is using our two equations. We know that 1 times A minus 2 times B minus 4 times C plus 0 times A times D should equal 0. Furthermore, we know that 2 times A plus 0 times B minus 1 times C minus 3 times D should equal 0. And we see how these equations have been encoded in the matrix. Therefore, the null space of this matrix will be exactly equal to the solutions that we saw above. All right, so I'm going to give you an example to work out, and you're going to find a null space just to practice what you've done before. I want you to find the null space of the matrix right here. So go ahead and take a second to find the null space. All right, now that you've had that opportunity, we know we need to row reduce it. So let's row reduce this matrix, and what we get is the following matrix in reduced echelon form. And so we have our two pivots, our two pivot locations, and therefore we see that the solutions are x1 is negative 26x3, and x2 is 7x3, where x3 and x4 are free. In other words, we get a matrix that looks like the following. And we can write this as the span of two different vectors. And so what we see is that the number of free variables is the number of vectors in the basis of null A. In other words, the number of free variables is equal to the dimension of null A. So this is one possible way of producing subspaces. Another way uses the column space of a matrix, which you are well aware of now. The definition is just like the one you saw before. So the column space of an n by n matrix which we denote col A, is the set of all linear combinations of the vector, of the column vectors. The columns of A. So, therefore, if the matrix A has the following column vectors, then this tells us that the column space of A is the span of these vectors. And just like the null space, the column space is a subspace as well. The column space is a subspace of Rm. So, and what this tells us is that if you can show that a set of vectors is equal to the column space of some matrix, then you've actually shown that it is a subspace. So another way of writing the column space of A is very helpful. It's all vectors B, so that B equals AX for some x in Rn. In other words, it's all the vectors that if you multiply A by a vector, you get an output vector. So the column space is the set of all these output vectors. So I'm going to write down a set of vectors, and you're going to identify the matrix whose column space is equal to the set of vectors I wrote down. Okay, here is our set of vectors, and we want to figure out what matrix gives us a column space equal to the set of vectors shown. So I want you to try it out, pause the video, and write down the matrix whose column space gives us this set of vectors. Okay, now you've had time to do that. What we do is it's really quite simple. We take this set of vectors and we need to break it up so that it's equal to some span of other vectors. So what we can do is we can break it up into vectors that involve the s, the r, and the t. So the r part is 0, 1, 4, and 3. The s part involves 2, 1, 1, negative 1. And the t part involves 3, negative 2, 0, negative 1. And therefore what this tells us is that if A equals those vectors over there that we've written down, then the column space of A is equal to the set of vectors up there. And therefore, this set of vectors is a subspace of R4. So this is, how you see the connection between this set of vectors above and the column space of matrix. And I want to make a quick remark, and that tells us that the column space of an M by N matrix is all of Rm if and only if this equation has a solution for all vectors B in Rm. So you can see how the column space having a certain dimension is connected to your matrix having a certain number of pivots. We've seen this before, but it's good to identify it in the context of subspaces. All right, last but not least, I want to talk about linear transformations. We've seen these before, and they are very relevant to the discussion at hand. So let's recall what the definition of a linear transformation is. A linear transformation is a function between two vector spaces. Okay, so it's a function from one vector space V to a vector space W that has the following two properties. The first property is that if you add two vectors inside the linear transformation and then plug it in the function, that's the same as plugging each of them in the function and then adding the outputs. And the second condition works with scalar multiples. If I scale my vector and then plug that into the function, that's the same as plugging my vector into the function and then scaling it. Okay, so we have some relevant definitions. The kernel, also known as the null space, of a linear transformation is the set of all vectors that map to 0. It's all the inputs whose outputs are 0. Okay, so that's the null space. And the range is all valid output vectors. Okay, so the kernel or null space are all the input vectors that go to 0 when you plug them in the function, and the range are all the valid outputs of my linear transformation or function t. So I'm going to give you a couple examples, and you're going to tell me what you think. I'll maybe ask you about the kernel, or maybe I'll ask you about the range. So let's look at the vector space V is the vector space of all polynomials. Okay, polynomials, sorry for that. And we're going to define a linear transformation defined by the derivative. So this is actually a linear transformation because, the derivative, if you add two things and take the derivative, it's the same as taking the derivative of two things and then adding them. Okay, so what I want you to do is find out what's the null space of this linear transformation and what's the range. So I want you to pause the video and think about what's the null space of differentiation. That is, what are the things that I differentiate and get 0? And also, what's the range? What are all the possible derivatives of polynomials I get? So pause the video, make a guess, and then we'll go over the answer. All right, now you've had that chance, the null space are all constants, all constant polynomials. Because these are the polynomials whose derivative is 0. No other polynomial has a derivative of 0. The range is just all polynomials. How do we know this? Well, if I want to get a particular polynomial, I integrate it and I differentiate it and I get the same polynomial back. So here is an example where you see a linear transformation in a vector space that's a little bit different than what you're used to. All right, so let's do one more example before I let you guys work on your homework for the weekend. So we're going to let V be the space of all differentiable functions. Technically infinitely differentiable, but let's not worry about that. We're going to let D be a different linear transformation. So we're going to take the second derivative of our function and then subtract off the first. So proving it's a linear transformation isn't so bad. But I want to know, what's the null space? So pause the video and then we're going to examine it. If you've taken differential equations before or you've seen it, you can probably figure this one out. Okay, now that you've had a chance to do it, we need to find a function so that I take the second derivative and subtract the original function, I get 0. In other words, this is the same as finding a function which is equal to its second derivative. If you think about it for a while, you probably are going to get e to the x. And in fact, you get e to the negative x as well. And so the null space is actually all functions of the form a constant times e to the x plus another constant times e to the negative x. So these are scalars or constants. All right, so these two examples have given you a little bit of familiarity with a vector space that is not what you might expect it to be. These are vector spaces of functions, and this is why we have to introduce the concept of a vector space. It gives you a little bit different feel of how general this concept can be, and shows you why our notion of having vectors before, coming from just n numbers in a vector from Rn, is a little bit limiting, whereas this more general definition of the vector space allows you to work in more, varied locations. All right, remember the homework's due on Friday, and let me know if you have any questions. Remember to post them first in the forum. Have a good day. Bye.